machine learning assisted quantum control in random environment. So here's the outlines. First, I will briefly introduce you the motivation of this project. Then I will introduce the random environment we applied in this case. And then we developed the two neural network-based machine learning to solve the quantum control problems with random environment, and then come to the discussion and conclusion. So the main motivation here is that we want to use the machine learning as a tool to construct some efficient quantum control in some random environment like impurities, noise. So that the idea is with some machine learning model that we can directly import the random environment and then automatically produce the optimal control policy or something like. So, but as we know, a lot of random environment in quantum physics. Here we choose the random potential. So the random potential is well developed in the past decades, even in the experimental, and the random potential can accurately produced in experimental, like in optical platforms, and even programmable the optical impurities. So more specifically, the random potential, in this case, the model is quantum particles in a radial potential with disorder. The disorder is induced by the random potential. And the random potential is a collection of impurities. A lot of impurity distributed in the coordinate space. And the random potential is the summation of a lot of impurities. Here, like for example, we design the impurity shape is a Gaussian shape, and with for example with impurities, and then we can the sign of each impurity is completely random distributed in the coordinate space. So basically, we can use a one-dimensional random sequence to represent one of the realization of a random potential. And for this kind of a definition of a random potential, the realization of a disorder is approximately like 2 to the power of n. The n is in impurity number. For example, if we have like 160 impurities, then the realization of a random potential is like 2 to the power 160. So it's a quite a huge number. And for this kind of random environment that we want to manipulate the quantum systems, like for example, radial quantum control problems, like quantum particles in a harmonic trap with this kind of disorder. The control task will be like an expansion of the quantum particles by manipulating the harmonic trap. So for this kind of, I would say it's quite, we are really familiar with this kind of control process. But with the disorder, the previously like shortcut to adversity is unavailable here. For, the reason is because of the strong disorder, the localization of density will appear in the system. For example, when we set the disorder, the strength of the disorder, then for the initial state, for different realization of a random potential, the initial state would completely different because of this Anderson localizations. So that's the problems. Like for example, we usually constrain some control policies. For example, we the initial and the final state is confirmed, then we design the control policy to manipulate the system. But in this case, the initial and the final state is not confirmed because of a random potential. So as I just mentioned, the realization of a random potential, the number is really huge. So it's really hard to efficiently manipulate the state in such kind of a disorder. And then another difficulty of quantum control with disorder it's because like I just said, the localization. For example, for two different kind of realization. For realization one, the initial state and the final state stick together. And in this case, we can easily implement some control policy to realize high fidelity control. That's our goal. But for realization two, you can see the initial and the final state, because of a localization, there's a huge gap between them. In this case, we barely can find control policy to realize the high fidelity control because this gap cannot be achieved like a high fidelity control. So that's because of that, it's really natural to think like first maybe we should preselect some realization. Then we can concentrate on the realization that it's able to find the optimal control policy things. But for realization two, we cannot find the control policy for that. So the first thing is the strategy would be with an arbitrary random sequence, which is represented by a random sequence. Then first step would be like a classification to classify the random sequence to select the random sequence that we want and abandon the unwanted cases. Once we confirm this realization, it's able to find the control policy, optimal control policy. Then we come to the second step with the regression and generate the optimal control policy. So the first thing jumped in my mind is we can directly use the gradient descent to find actually optimal control. For example, with the typical with some how to say for example for one typical particular the random sequence realization, we use the gradient descent with some constraint and directly find the optimal control policies. But for this kind of methods, we have to use 100, for example, here I use 100 parameters to determine the control policies. So in this case, if we use a gradient descent to constrain the optimal control policy, for the second step, the regression part, the input would be the random sequence, but the output is 100 parameters, which is represented for the control policy. And we can see for the regressions, for example, we use the neural network to do regression. The output would be 100 parameters. It's quite difficult to converge the cost function, and then it's not quite efficient for this case. The output, the number of particle, the parameters is too large, 100. So we come to the strategy two. For example, we have to decrease the parameters of regression. So how about we set polynomial answers? For example, the three order polynomial answers. So for this kind of control answers, the free parameters would be 2. So basically, for the second step of the regression is to find the optimal control policy based on the control polynomial answers. So the output of second for the regression would be 2. 2 parameters is quite simple to converge the cost function. So the idea is we use the control answers with 2 free parameters and set the constraint of A1 and A2. In design the constraint, we find the optimal control policy, which is represented by two parameters. Then we can produce the better performance in the regression part. But even for the two parameters, like because the amount of random realization is quite huge, so it's really hard to generate the optimal control policy. And the answers here, the role for answers is like to help the classification process to label the realizations. Like it's quite straight. Like with the control answers, we can quantify the criteria of classification, like what kind of a random sequence is we want, and what kind of is we don't like. So the law of answers now is not the key point of constraint the optimal control policy, because you always ask why use the answer, why use these simple control answers, because it's not of course it's not the optimal solution. But here the answers is the tool to label this random sequence, help us to select the random realizations. That's the point. And I will discuss this later in the discussion. So, like I just said, with this polynomial control answers, we have to set criteria of optimal control policy. So first, for each realizations, we set the constraint on A1 and A2, and in this range A1 and A2, we can always calculate the maximal fidelity control policy. So this maximal fidelity control policy, we call it optimal control in this range of parameters. And for arbitrary realizations, the maximal fidelity and the maximal value of this control function, we set two criteria to quantify this realization. We call it high fidelity if this maximal fidelity is larger than some critical point, and the control function is smaller than some value. Then we set this to satisfy these two criteria. So we label it as wanted, and otherwise it's unwanted. So here's the feasible and high fidelity. And before proceeding, we want to give a class on the disorder-free models. That if without any disorder is quite simple. It's a harmonic oscillator, and the solution of ground state is analytically expressed at equation 3. And for any arbitrary control policy, the fidelity can be analytically expressed as equation 5. And in such kind of control polynomials, the fidelity can be precisely calculated in the subfigure C. And okay, so as I just mentioned, for different realizations, the maximal fidelity corresponds to the A1 and A2, the optimal control policy. We local the different realization in this figure. The background is disorder-free, and we can see for some cases, for some realizations, the fidelity in the case with the disorder is higher than the case without the disorder. So the right one is the feasible, to clarify the feasible property of control function. The figure B is a control function is reasonable, and the figure C is quite large. Is is unfeasible in reality. And then we come to the machine learning and to neural network. So the first thing is let's record the whole process. Like we got a lot of random realizations. Our idea is use some black box and you input the random realization and output the optimal control policy. So, and in this black box, there are two parts. The first one is classification to pre-select the realization to abandon the realization that unable to produce the optimal control policy. And the second is the regression part. The regression part is the input is wanted realization and output is the control policy, which is represented by the two parameters. And the first thing is we extended the input. As I just said, the input is a one-dimensional random sequence, and we firstly extended to two dimensions. So the reason why we did this these two dimensions is because it's quite straight to understand. Like for neural network, if we amplify the feature of the random sequence, use the two-dimensional neural network. For example, the CAN is more powerful than one dimension, but of course with larger parameter size. And the workflow of this process, we import the random sequence first, extend it to the two dimension, come to the first neural network. We use the convolutional neural network to classify the random sequence. Then we use the second neural network to do the regression. Finally, we can automatically produce the control policy. And here's the detail of classification and the regression. The input of classification is a two-dimensional random sequence. The output is a binary classification to select the random sequence. And the second neural network, CN2, is for regression, and the input is the wanted random sequence, and output would be optimal control policy A1 and A2. And we apply the different structure of neuron CN. For the CN1, it's quite a regular sequential structure, and for CN2, we implemented the ResNet, this special agriculture. And for CN1, we define the accuracy. The accuracy, of course, the accuracy of classification. And for the CN2, we define the quantity like fidelity deviation. So the fidelity deviation is like capital F max is exactly produced by the maximal fidelity in that in range of A1 and A2, and F prime is represents to the prediction of the second neural network, the predicted control policy. Then we use this predicted control policy to calculate the fidelity. So the fidelity deviation. And the cost function, of course, for the classification is cross entropy loss, and for regression it's quite normal and common. And here's the machine learning outcome. For the classification, we can see the accuracy more or less larger than 0.997, and for the regression, the fidelity deviation is quite small enough to neglect it. And then we want to verify this whole black box. We generate 100 data out of this training data, then to verify this two neural network to find the result. We can see the fidelity deviation is quite more or less smaller than it's acceptable result. And so far we use the supervised learning. We constrained the database and training two neural network. This two neural network can efficiently, once you input the arbitrary random sequence, then output the optimal control policy. And we come to the discussion. The first things we want to discuss is the generality of this model. We choose the different time and different control process. The result is quite reasonable. And the second thing is, as I just mentioned, the different when we use the two dimension, as we can see, whenever the accuracy and the fidelity deviations outperform than the one dimension, is easy to understand because for the two dimension, the parameters in the neural network is larger than the one dimension case. Use more computation source. This source, and then the hyperparameters, the main property of neural network, we have to consider the exploitability and the generality. So we change the hyperparameters in the second neural network to change the structure and sorry. Then we want to discuss the law of gradient descent. Like I just mentioned, why we can use this polynomial answer to say it's quite it's enough to use the polynomial answers. We can see if we treat the gradient descent as the actually optimal control, and the answer is some local optimal. And we compare these two results, we can see the fidelity difference is it's a little bit, but for the second neural network, the polynomial is 2 parameters, and for the gradient descent is 100. And so that's why we use these polynomial answers, because you want to improve the fidelity a little bit by using gradient descent, but the cost is the second step regression is completely disaster. That's why we stick to the polynomial answers instead of gradient descent. And the reason why was that is because of the localization. You cannot change the physical property. The localization is dependent on the realization. You use different method of gradient descent control answers. Is the role of this different method is to classify the realizations. That's the reason. So no matter different answers, it cannot change the localization appears in different realizations. And we also compare we want to show the advantage of our neural network, convolutional neural network. And it is clear, like we use regular deep neural network, it basically cannot converge it to. So yeah, for the gradient descent, of course, because the classification part is the same, like it's a binary classification. So the gradient descent and the answers, they show the same result. And for regular neural network, you can see the accuracy or fidelity deviation not good. So that's because we use the convolutional neural network to classify actually the figure, like we extended one dimension to 2 dimension. That's the key point of why we use 2 dimension. Like because convolutional neural network is especially for the image classifications, and we use that properties, and we extend one dimension to 2 dimension to. So that's why the result is better than regular neural network. And the last thing is the interpretability of a convolutional neural network. As we all know, the neural network is quite basically a black box. We always use it but not understand it. But here, phenomenologically, we extract the feature map from the neural network. And coincidentally, we find that the final state, the density of a final state is related with this feature map. Then we can phenomenologically to see some, it's a way to understand why the neural network make a decision like to classify the realizations. So that's what we call it the interpretability of a neural network. It's the input is a two-dimension random sequence, and after some neural network, some calculations, then we can deprive the result. It's actually is the same size of the random sequence.
So the square below is the initial data or the final data?
The last layer. Yes.
Also, the final data. So it's the final data with the same two axes.
Yeah.
Okay, and then the upper.
This is the density of system, the wave function of the final state.
So you are summing in one of the x-axis, and this is the accumulated, or how? So what is in the upper part? What is in the x-axis?
Yeah. The upper is the coordinate of a trap. This is the coordinate, but and the random impurity is distributed in the coordinate space. So it's basically in.
But how do you?
You mean how to obtain this feature map?
Yeah. No, the upper one. The
upper one. Upper one is the numerical result of a wave packet. Yeah. So for different realization, there are a lot of these different.
So it's the modulus of the wave packet.
Sorry.
It's the modulus, the probability distribution.
Yes.
Okay.
Yes. And we come to conclusion, which if the optimal control of the quantum particle in random potential using a machine learning system technique. And of course, I want to emphasize the ansatz. The law of ansatz here doesn't matter like a polynomial 3 or 5 order. Is the law of the ansatz is to help us to pre-select the realizations and the gradient descent and with gradient descent and simple polynomial answers, they show the same result for the second neural regression, because the function of the answer is to pre-select the wanted realizations. So, and then we also discussed the interpretability of theorems. And I'm quite sure that our method can implement in the, for example, in the to predict the localization of this random potential. It's for sure. And our methods supervise the efficient way, like a different random environment, and then we can use the different process. We use the same process to handle this kind of disorder, and to make sure the actually efficient model to produce the optimal control policy. Yes, thanks for your attention.
I have a question regarding slide 12, this one.
12, yes.
In the end of the paragraph, can you read what I can read it? Okay. Interestingly, for a given set, the fidelity in the presence of
disorder
can be higher than that for the
disorder free.
How is that possible? Because couldn't you add noise as a control sequence in order to simulate that disorder? environment.
You mean you think it's impossible, right? I can explain this. Why the disorder? Like first we can see this plot, the left plot. The square and the circle is all the case that maximum fidelity is larger than 0.9. But you can see the background is disorder free. So you can see the background, the fidelity is more or less like 0.7, but this circle and the square is larger than 0.9 with the disorder. But why it happens? Because we can see the localization. For some cases, for example, realization 1, in these cases, with disorder, it's possible because of disorder, we can achieve a higher fidelity than the case without the disorder. Like for realization 1, we can use the control, the polynomial ansatz, because they stick together, the disorder will affect the control process. I think it's possible to produce the higher fidelity than the case without the disorder.
It's because you are restricted to a polynomial ansatz in this case. So the statement is true in the case where you are
yeah, even with this simple polynomial answer, it's quite simple, even with this simple.
Very small question, very last question. I didn't, because I have to go to my classes, so I missed part of the. I don't understand the role of the second convolutional neural network.
The second.
Yeah.
Okay. So for the first, it's quite straightforward, like we classified the realization. For the second, because we want to produce the control policy, right? And firstly, we classified the realization that we want, and for this wanted realizations, what's the optimal control? Policy is polynomial, right? Polynomial answer is dependent on the two parameters. So we want to train like input is wanted realization, output is the polynomial polynomial answers. So that's why we want to do the regression to training the second model.
So the second convolutional neural network is just to obtain the parameters, three parameters of the polynomial answer.
Yes. It's based on the polynomial answer. So that's why we choose the answers, because for the regression, the output if we choose the gradient descent like 100 parameters, but with a little bit improvement of fidelity. So we use the two free parameter dependent polynomial to make sure the second neural network works.
So the second neural network cleans the noise somehow, or extracts information, retrieves information about the noise.
Yes.
First one do the task.
Yes.
The classification task.
Yes, exactly. Yeah.
So the choice of answers will also affect the prediction result. So if you choose other kinds of answers, maybe you will get some suboptimal results or other results, or maybe if you increase the order of polynomial answers,
yes,
more parameters, more freedom, then you will also maybe enhance some.
Yeah, yes, that's a question, a good question. So that's why I presented the gradient descent and the answer. You can treat these two methods is a bound of the control answers. Like for gradient descent, is quite perfect control answers, but for the three other parameters, It's the simplest control answers. Then I plot the difference between these two answers. You can see a little bit different. So that's why I said the choice of control answers is not the key point in this case. Even with, for example, you use a complicated answers, but of course it's not good enough as the gradient descent. Even for the gradient descent, the improvement of the fidelity is quite small. So don't bother choose different kind of control answers because
It's not very sensitive.
Yeah, I think your question is mostly depend on the single random realization. For a single realization, for one particular random realization, you can always use optimal control or the more polynomial answers to optimize the trajectory. But the point is that with this thousands random realization, you need two neural network. For instance, if you optimize the first one, and you will get fewer input for the second one, and the second quality becomes worse. You think the point? So this is the input output is so relevant between these two neural networks.
Yeah, because these two neural networks.
You only think one random. You see, suppose you have one random realization, you can always find the optimized to optimize one trajectory. But here we want to look at the general control point with thousands of random realizations. That's why we need the first one to pre-select the random, which will give us the best solution. And the second, we will do the optimize. But why he translates to use two neural networks and not the deeper one?
Yeah, I just.
That's the point.
Yeah. Yeah, I compared the result of radio deep neural network, and because our the input is like for one dimension is 160, for example, input, and the way extended to the two dimension is more or less like a figure. So it's reasonable that the convolutional neural network is especially for the image classification. And the result, I compare the radio deep neural network, you can see the accuracy of radio neural network is not good as the convolutional neural network.
But what happens is instead of large convolutional neural network, you use, so instead of a larger convolutional neural network, you use a quantum encoder before the convolutional neural network. That would give the data.
You mean before you use the first neural network, we can.
An encoder, a quantum encoder that can link somehow, and this is the income of the quantum encoder of your second convolutional neural network. In such a way that you just.
Yeah, but the point is the amount of the realization is like. Because of that, then we use the to build a general like a classifier to classify these realizations. Yeah, that's because. Yeah.
Thank you again.
Okay. Thanks.